But what I'm going to do is I'm going to also show you a bit of a shortcut. Okay, it's called the DI method, and I came across this, and you know what, I thought, this is too good. This is too good to let go. It's sort of it's like I say, it's a shortcut. You don't have to memorize this formula. Okay, you don't have to memorize it. I mean, you could and you should, for sure. But I'm going to show you what the DI method consists of, how it looks, and how we go about finding an integral without actually memorizing and using this specific formula. So I'm going to do the same question, okay? And I'm going to outline the DI method here for you, okay? So you want to copy this down, same one we just did. But the DI method, in the DI method, what you do is you make two columns, okay? And you make a D column and an I column, DI method. Now, what does the D column stand for? Well, it stands for derivative. Okay, you want a derivative column. And what does I stand for, you figure? Integral. Okay, so derivative and integral. We're going to make two columns. Now, why would we do this? Maybe you can see why we might set this up this way. Notice how we have one of these functions we took the derivative, and one of these functions we took the integral. See that? In order to set this up originally. So we're taking this right here and this sort of action, and we're putting it in kind of a short form chart method. Okay? Because one of these we're going to take the derivative of, and one of these we're going to take the integral of, and so we're going to keep track of all that here. And there's a couple other little things that will help us. So two columns. Next thing you're going to do is put a plus sign in the first row. I'm going to make a line there for now. We won't make lines in the future. Second row, minus. Then plus. Then minus, and keep alternating. Now you only have to do 3 or 4 rows here for some of these simpler ones, okay? So this is the DI method, and this is like a sort of simple type. So type 1, I'm going to call this, okay? What we want to do is we want to place one of these functions here, one of them in the derivative column and one of them in the integral column. Okay? Generally, if you have just a polynomial or something like that, that's going to be the one you want to differentiate. Why? Because if you differentiate a polynomial, it only takes a few times of differentiating, and you're going to get down to 0, which is actually going to be really good in this method. So I'm going to put x right here. X right here. So that means that I'm going to integrate e to the x, and that's what you do, okay? Now, in this chart, this right here, a row is kind of like an expression for the integral. Notice how I have positive x times e to the x. Positive x times e to the x. So a row represents an integral, okay? Okay. So what I'm going to do is I'm going to take the derivative of x, which is going to be 1. And I'm going to take the integral of e to the x, which is going to be e to the x. Okay? And like I said before, the key to this is you're going to, for type 1, for the simple ones, you're going to keep differentiating until you get a 0 for a derivative. And I'm going to complete this row by taking the integral. And again, e to the x is so wonderful. Okay? So differentiate down to 0. That's type 1. And that's going to be the majority of your simple integration by parts integrals. Now what do we do? Well, here's the tricky part now. Is this even tricky? It's not tricky. So remember, a row is an integral. That's going to be important when we get to type 3, I think. But for now, the easy ones, what you do is this. You now take a look at the top one here, and you connect it with the term that's in the second row on the integral side. Now, why would I do that? Well, here's a function and here's its integral, or here's a function and here's its derivative, a derivative of the other one, or whatever. So we're connecting, remember, with the formula here. Where is it? We're connecting a function with a derivative with a function. So that's what we need to do. We need to kind of like partner these up. And the simple thing is we're going to connect these right here on the diagonals. Now, I could keep going. I could keep going here on this side, but what happens when I partner up a 0 with something? Okay, that's when we know we're going to stop. Because we're going to multiply these two terms. Multiply and multiply. So once you get a 0, you can stop. All right. Okay. Now I know this has nothing it seems like it has nothing to do with calculus, but this is a great shortcut, okay? It's a great shortcut. So what we're going to do now is we're going to include the signs here with our products that we've outlined. So this integral is actually disappeared on me. Let's get that program going again. Thanks, OneNote. That's a signal for me to take a sip of coffee. Okay. That's not good to happen twice. Okay. I love technology. I love technology. Okay. Okay. Equals. Don't die on me. All right. So I take a look at this sign and the pairs now that I've circled, and I go x times e to the x. And then I move to the next pair with the sign. Minus 1 times e to the x. Plus, well, here we go. We got a 0. So 0 times e to the x, right? So what do I have? I have, oh, and then plus c, I guess. Plus c. I have x times e to the x minus e to the x plus c. And this is exactly the same as what we got up here. Okay? Oops, did not mean to do that. Now you can factor and simplify, of course, but see how slick that is? How that works? Okay? It works very well. So I'm kind of setting one function up as a derivative and one function up as a regular function, and then I'm just kind of moving down the list according to this right here. Okay? So if this is a function and a derivative, then I need to write the function and the integral. Function and the integral. Wow, that's this part. Then I need to subtract. Well, here's my negative sign on my chart. I need to subtract. I need to subtract the integral of 1 times this one, e to the x, minus 1 times e to the x. Well, what's the integral of e to the x? Well, it's 1 times e to the x. So minus 1 times e to the x. And that's actually the evaluation of this integral. So remember, rows are integrals, right? Rows are integrals. So so minus the integral of 1 times e to the x would match up with what this term would represent. So the chart is helping us. Okay? Online class, you guys that are watching, do you have any questions? Any questions about this DI method? Go ahead and fire them away in the chat box. Okay, so seeing no questions here, let's take a look at another integral. This one looks a little bit more complicated, doesn't it? Ooh, integral of x times cos 3x dx. So go ahead and write that down. I do have the table of integrals there, just so we can kind of, when we do our DI method here, we have to integrate some things, so we'll take careful note of that. But just write this down and we'll see if this is a candidate for integration by parts, first of all. So you might say, okay, I'd love to do u substitution. That is pretty easy. So if u was 3x, okay, u equals 3x, du equals 3 dx. Well, I could put a 3 in there and put a 1/3 out here, but I've got this pesky function. I've got a multiplication of an x term. That's no good. I can't just whip up an x like that. So this is not a good candidate for u substitution. Okay? Now everyone needs to see that. You guys understand that, right? So if you think u substitution, you get into the process, you got an x that you can't account for, move on. Integration by parts now. Let's try that. DI method. Well, Mr. Maxwell showed me a DI method. That was pretty slick. Why don't we try that? Okay. So DI. What am I going to do? Let's do it over here. DI. Now I told you I'm not going to do rows anymore. I'm just going to do plus minus plus minus. Okay. So here we go. Which function am I going to differentiate all the way down the list, and which function am I going to integrate as I move down? Well, remember, polynomial functions are pretty good ones to differentiate because they get you to 0 pretty quick. So polynomial functions or polynomial terms, that's probably the one you're going to choose for the one to differentiate. Okay? Now, would you get really messed up if you got these wrong? No, it might be a little more challenging to integrate. Okay, so the integrating might be a little more challenging. You're gonna have lots of fractions. You're gonna have lots of different things. Not a big problem. For these simple ones, it really doesn't matter too much. So then cos of 3x is going to go over here. Because cos of 3x, I mean, it's not a slam dunk to integrate either, but you guys know how to do this. Okay? So really, I've just set up my integral here. See that? And I'm going to use this chart to find derivatives, integrals, and we're going to match these up just perfectly. Okay. Derivative of x is 1. Derivative of 1 is 0. I know I can stop at this row. Okay? All right. Integral of cos of 3x. Integral. The integral of cos is, well, you should remember, but where's cos? Oh, the integral of cos is sine. It is. So we're going to have sine of 3x. Now remember, if we were to take the integral of this, sine of 3x would be cos of 3x times 3, but I don't have a times 3 there. So I need to counteract that chain rule by doing 1 over 3. You guys remember that? So the integral of cos of 3x is 1/3 sine 3x. With me? Okay. Now let's do the integral of this again, because we got to go one more. Shouldn't be that big of a deal. What's the integral of sine? Well, here's the integral of sine. It's negative cos. Okay. Negative cos. I've got that 1/3 there. I got to keep that 1/3 there. And actually, I'm going to have to counteract the chain rule again. So I'm going to have to put another 1/3 there. Cos 3x. Okay? So that's going to be negative 1/9 cos 3x for an integral. You guys see that? And because this is a 0, I can stop. Because whatever I put down here, this is going to be times 0, right? This is 0 again, times 0. It doesn't matter. These are all zeros underneath here, so I can stop. All right. You guys with me so far? Okay. Okay, so now we have the process of writing out what the explanation is here, or how is the integral defined now? Well, I do this. X times 1/3 sine of 3x. So I've got 1/3, I'll just put the x there, sine 3x, minus 1 times minus, or negative 1/9, so that's actually a plus 1/9 cos 3x, plus 0, or plus c. So in this case, here we go. This is our answer, and I kind of didn't have enough room for that. But this is the integral for the answer for the integral. Okay, that's the indefinite integral there. When you evaluate that, simplify that. Okay. Again, this is the DI method helps us because it's going to get a little bit messy when you're using that formula, okay? So the DI method, the chart is based off of the formula. All right? Okay. I'll tell you what, why don't you take a moment and integrate this, okay? Find the integral of this. Go ahead and do this yourself and see what you come up with. I'll give you a few minutes to do that. All right, so this is what I would do. Again, this is a polynomial term there, so I'd make that my derivative column. I'm going to take the derivative of that. I'm going to integrate sine of x. Okay? So the derivative of x squared is going to be 2x. The derivative of 2x is 2, and then 0. Right? So we go all the way down the list there until we get to 0 and we stop, and then I need to go 1, 2, I need to fill in 3 columns here. So the integral of sine x is going to be negative cos x. The integral of negative cos x is going to be negative sine x. And the integral of negative sine x is going to be positive cos x. So once we have this chart figured out, then the next part is really easy. Of course, we just do our diagonals, starting with the very first term. So this integral is represented by writing x squared times negative cos x. So I'm just going to write negative x squared cos x And then I'm going to, I got a negative and a negative, so that's going to be a plus 2x sine x. Okay, so that's this one taken care of. And finally, plus 2 cos x. Plus 2 cos x plus c. All right, so there we go. That should be our solution for this integral. Now, integration by parts is amazing when we have two functions multiplied together. There's no way that you would be able to just in your head, and obviously not by use substitution, but you wouldn't come up with this simplification of this integral. And so hopefully that DI method is proving useful to you. Okay, let's end off with a bit more of a challenging one here. Secant squared. Now, secant squared, you may not remember what the integral of secant squared is, but we're going to want to differentiate t, and we're going to want to integrate secant squared. So why don't you go ahead, and I will put this little chart up here so that you can have a reference for that. Why don't you go ahead and see what you can do with this one? Okay, a little bit more challenging. This is what we'll kind of end this little lesson on here today. Okay, so if we set the derivative to the t and we set the secant squared to the integral, now this integral chart here is not going to help us for secant squared, but you may remember that the derivative of tan of theta is secant squared theta. So the integral of secant squared is tan. So this row here gives us a tan of t. The derivative of t is 1, and I usually like to do a whole, I guess, column at once, but the derivative of t with respect to t here, right, is 1, and then we have 0. So what is the integral of tan? That's where your chart comes in. I'm sorry, I'm paused. So we take the integral of tan, that's where you need this chart for. So the integral of tan is actually negative ln of cos x plus c. Crazy, huh? So negative ln of the absolute value of cos x plus c. Okay, and because we have a 0 here, that's as far as we need to go. So the integral of t times secant squared t is actually not as hard as it maybe seemed to be once you do the DI method here. So it's t tan t, right, plus, we got a minus times a minus, plus 1 times the ln of cos x plus c. And that's where we're going to leave it. Okay, so again, a complicated integral using the DI method, we are good to go. Okay, so let's just review this lesson so far. That's type 1. That's the DI method. Those are some of the easier ones, the type 1 methods. But integration by parts is a way that we can integrate when we have something that has come from a product. Okay, so the product rule is undone by integration by parts. And here I did the product rule by differentiating, then I integrated everything and rewrote the integral. So we get an integration by parts. One of the versions looks just like this. You'll see in your textbooks that this formula is used here in this way, and I've also shown you how to use the DI method. Okay, so that's integration by parts. That's method 1 or type 1, and I'm going to show you what to do with more complicated ones, or when you run into ones that don't end in 0, for example. Okay, so if you don't get to 0, what do you do? Okay, so there's two different types that we're going to explore in the next lesson.